Every time we said, oh my God, this is going to be a gangbuster, the 3105 is going to be overflowing, let's go get a room over in Moffett or over in Barrows Hall. It's a little bit like what happened in Napoleon's army marching to Moscow. It went down by a factor of 10. So anyway, but still we had a good crowd here. Had we tried to do this in 3105, we would have had 80 people or something. While we're waiting a little bit, I just forgot, I will make a shameless pitch. Since today, this is the visit day of the people we've admitted here. The one important thing I forgot to tell you, completely irrelevant to the colloquium, is, and I mentioned it to Samantha here, one of the greatest things about this department, and we've actually had people come here and visit and see this thing and discover this thing and decided, I'm going to come to graduate school here. We have the best student machine shop in the galaxy. Most universities, for safety reasons, have just basically given it up. We don't want you guys in there. This is a problem. It's a hazard. We've actually expanded it. We've embraced it. We actually have, the mechanical engineers have a shop down in the first floor. And if you have time, we'll show it to you afterwards. That is an immense cavernous room, and they're expanding it, that has 10 banks of lathes and machine shops. They have wire EDM, they have laser, water jet, CNC, everything. It's a garden of delights in there. 5 fantastic guys who just love teaching. Staff people are there from early in the morning to early in the evening to help students. And they train every year 500 people. You go in there, freshmen who come to me and attach themselves to my group, I get freshmen trained as machinists. They're worth their weight in platinum literally within a month. Okay, they go in there at 8 o'clock. By 2 o'clock in the afternoon, they do a little final exam, which is a little widget you make from a blueprint. And they're good. And it really works well. And that's because at places like research institutions where you came from, like here, our mechanical engineering students build, full-size solar-powered cars to take part in national competitions and so forth. And they build that with their own hands. This is a great place to come if you want to be an experimentalist or work in a machine shop. Check it out. I'll show it to you if they're still open when we go back there. So let me introduce our speaker today, who's maybe a bit bleary-eyed, just had their 3rd baby. Congratulations to Adam. Adam and I actually did not know one another, but we were actually part of the same high-energy physics experiment. I'm a unreconstructed high-energy physicist. Adam actually was rehabilitated and has actually had his useful function in life. He's now an assistant professor at University of California, San Francisco, one of the really premier medical schools in the world. We were part of the PEP2 B factory. It was a high-intensity electron-positron collider built at SLAC in the late 1990s and used up until about 2008. I actually left the experiment after being the Livermore project director for many years. And you joined at Santa Barbara and finished your thesis in 2006. So Adam is a person that came through a career in high-energy physics. You worked on ATLAS afterwards, did you? Mm-hmm. At Brookhaven National Lab, and then saw the light and said, medical physics is really cool. He's going to tell us about his own itinerary today and about what it is like for a student to get involved in and move into a career in medical physics. He's going to tell us what medical physics means, what's radiation oncology, what's non-invasive imaging, and all this. Things have changed. The national accreditation standards, CAMPEP, have actually ratcheted up their standards. This is a marriage made in heaven. There is right now a working group of which Adam leads. Kai has been a backbone in his group because we've been doing a lot of joint research with UCSF on medical imaging for a long time. And the time came to say, let's do a joint PhD program because they absolutely need our department as a pipeline to provide the field with medical physicists, because the jobs are just going begging. So without further ado, I won't tell you too much more about him, but he's going to tell us about his own itinerary and tell about the program that we've got cooking. So take it away.
All right. Thank you, Cal. All right, so I had a few movies in this talk, and I think they crashed when I put them on the big screen. I don't know why, so at some point if I skip a slide or two, that's why. I don't want to crash it in the middle of the talk, so bear with me on that. I think we'll do fine without them. Okay, so we're going to talk about the frontiers of medical physics research at UCSF, and then a hint at what we're building here with this joint program in medical physics and nuclear engineering. So in order to get into that, I want to talk about what is medical physics, what is the nature of scientific research in the field of medical physics? What avenues are UCSF faculty pursuing? Who are medical physicists, where they come from? And can I, as one of you, pursue a career in medical physics as a nuclear engineering PhD student? So first off, let's talk about what is medical physics. Okay, so the American Association of Physicists in Medicine is the governing body. So if you want to do some searching on this stuff, AAPM, Google that. AAPM.org is a website. A lot of the material about the kind of descriptions of what we do as medical physicists is on there if you want to do some perusing. But medical physics is definitely an applied science concerned with the application of the concepts and methods of physics to the diagnosis and treatment of human disease. It's a very broad definition. What does this mean? Well, the essential responsibilities of a medical physicist in clinical practice is to assure the safe and effective delivery of radiation, to achieve diagnostic or therapeutic results as prescribed in patient care. And by patient care, it's generally under the care of a physician. But because of what these physicians are trying to do in order to treat your disease, most of the time cancer, there's a lot of technology involved. Because there's a lot of technology involved, they realize that they need physicists to kind of to integrate the field with this technology that's going to provide these therapeutic solutions. So the medical physicist also performs and supervises the technical aspects of all the procedures necessary to achieve this objective. So physicians are working very closely with physicists to create these diagnostic and therapeutic solutions for patients. In general, if you work in medical physicists, there's a normal breakdown of you've got clinical service and consultation, you've got teaching and mentoring, research and development, and administration. Obviously, those very broad subjects. But if you're on, for example, a faculty position in medical physics, then you're going to take on all of these. If you're in a clinical position, obviously, you're not going to have as much teaching and mentoring. But the type of jobs that you get are going to take some admixture of all these components. So let's focus a little bit on what we mean by this here. So what we're going to be doing as medical physicists can be broken down into a few things. Protection of the patient and others from potentially harmful or excessive radiation. So we want to be aware of what's going on when we're delivering radiation to those patients. We establish adequate protocols to ensure accurate patient dosimetry, measurement and characterization of radiation, determination of delivered dose, advancement of procedures necessary to ensure image quality, development and direction of quality assurance programs. All of these are the kinds of things that we do. Assistance to other healthcare professionals in optimizing the balance between beneficial and deleterious effects of radiation, compliance with applicable federal and state regulations. So it's a very applied science. Okay. So medical physics can break down into 4 subdisciplines, and I just want to go through, again, this is just the basics of what we do. There's diagnostic medical physics, which deals with often in radiology departments. They deal with all kind of imaging modalities. So MR, CT, mammography, ultrasound, positron emission tomography, PET scans, fluoroscopy, angiography. All of these things are usually used for diagnostics, for determining what kind of disease you might have. Medical physics fits right in with that in radiology. Then there's therapeutic medical physics. This is often found in radiation oncology departments, where I am. And that is measuring and characterizing radiation, determining delivered doses to patient, because photon going into water, which is basically what we are, delivers a specific amount of dose depending on a lot of different factors. We have to understand that. Establishing adequate protocols to ensure accurate patient dosimetry. Collaborating with radiation oncologists, like I said, my position is very closely related to physicians. I work with them every day to design individual treatment plans for patients. Monitoring equipment and procedures to ensure that the patients receive the prescribed dose and the radiation at the correct location. So that's therapeutic medical physics. Then there's medical health physics. Generally, it's also called nuclear medical physics, and it's often in a radiology department. And this is radiology done inside out in some sense. So you have ingested radionuclides like thallium or iodine or technetium, where they map the physiological function of what's happening in your body, not just the geometric orientation of your anatomy like you have with an MR or CT scan. So in here, you could do photon detector development, develop nuclear imaging and radioactivity measurement equipment specifications. Some much more practical things like designing shielding needed to protect the patients and workers who are delivering this radiation at hospitals. These are tasks that you would do as a medical health physicist. And then there's nuclear medical physics, which is really the physics of radiation protection. In this case, and this is very practical, and these jobs are generally in hospitals, and you're concerned with the recognition of, evaluation and control of health hazards to permit the safe use and application of ionizing radiation, designing shielding again, develop, manage, and evaluate radiation safety programs. So these are the 4 branches of what it means to be a medical physicist as defined by the AAP. There's a lot of flexibility in these. You might be 1 or 2 or 3 or 4 of these things, but these are just the categories that it breaks down into. Okay, so in a nutshell, medical physics, what's that? Well, we have imaging to diagnose and visualize cancer. We have modeling radiation dose delivered to tissue, developing optimization techniques for dose delivery, external radiation delivery methods, internal radiation delivery methods, and it's very much an applied field. So these all kind of encompass what we're going to do as a medical physicist. So what careers in medical physics are available? Well, there's commercial. If you get a specialty in medical physics through a nuclear engineering program, then you can go and get a job down in Silicon Valley and some these medical device companies who are developing techniques to deliver radiation to patients. You can go into a clinic. You can get a residency. You can apply for residencies. You can get a residency and do a very clinical job where you're working in a medical clinic to take care of all the technology. You can go academic. And I kind of do a joke here that an academic, 50% of our time is research, 50% is clinical, and 50% is teaching. So, that's generally true, I think, of a lot of academic careers. The same thing goes for medical physics. Just because we have that clinical duties actually takes up, a significant amount of time. It can be weighted more or less depending on what your position is. And I can go into that a little bit more. For example, UCSF, our faculty are both clinicians and researchers. We are a hybrid of both. That's how our jobs are defined. If you go down to Stanford, you either are clinical medical physicist or you're applying for big NIH R01 grants and you're a research specialist. So they have a segregation, but it depends on where you go. You could have both. You could have one or the other. Okay, so that's a very brief overview of what is a medical physicist. So now let's go into what is the nature of the scientific research in the field. What kind of things do you do if you're a researcher and you're doing work in medical physics? All right. Well, let's see. There's radiology, and if you work in radiology, then you want to see the cancers. That's what radiology is all about. We're developing technologies to see cancers. Now, traditionally, imaging requires photons, radiation. We don't necessarily need photons, but that was a relatively new technology, right? Back in the day, you used photons, you delivered them to a patient, you take an X-ray, okay? Now, that delivers radiation to the patient, so obviously that's not the most optimal thing in today's technology, so maybe we can develop new technology. So one of the big things that a radiologist did was they developed MR. So MRI was a way to image patients without delivering radiation to the patient. This is just broad examples of what kind of things are happening. But what's the next step in imaging technology? What's that next big thing that you can do to create an even better environment for imaging the patient and detect cancers early? Mammography, for example. If you can detect breast cancer early, then you can treat it. You can treat it very effectively, but you have to detect it first. So what's that next technology? So how can we distinguish between healthy tissue from cancers? That's very important when you get to the next stage, which is therapy. Okay. So, and can we make the technology that can discriminate these two? So these are the kind of broad questions that you're asking in radiology. Now, the next phase in cancer therapy is generally killing the cancer. Once you know it's there, how do you get rid of it? Well, killing the cancer is the job of radiation oncology. So in general, radiation kills the cancer, and we want to get as much radiation to the tumor as possible. This is kind of an old picture of way back, one of the first radiation detecting devices called the radium bomb. Okay? So they put radium in this device here, and they had it on the patient. So the patient in here who has a tumor on their neck, for example, there's radium in here. This guy's standing kind of far away because you have an 1/r squared effect for radiation protection. So this was their radiation protection of the guy who's delivering the radiation, just 1/r squared. Now, obviously, there's some lead in this as well, but when you come to look at what we do today, this is a little bit kind of crazy. We would never even do this. Who knows how long this guy survived if he had to treat a lot of patients doing this, okay? But that's the idea. We want to get as much radiation as possible. Back in the day, they didn't know side effects. But obviously, we learned that radiation, I mean, Marie Curie, the famous, the pioneer of radiation, all of these people had problems with their hands. By the end of their life, they had a lot of problems with their hands because they were dealing with this radiation and they didn't know the effects. Okay, so there definitely are effects. Radiation kills healthy cells as well. So how do we best balance this? A lot of what radiation oncology physicists do is figuring out how to deliver a lethal amount of radiation to a tumor while giving sublethal amounts of radiation to all the other tissues around it. That's a huge problem. It's a very big question in radiation oncology, and medical physicists are trying to solve that problem every day. So how do we get therapeutic dose to the tumors without killing healthy cells? Well, when you look at modern technology, rather than using the radium bomb here, by just dumping dose, we do it very precisely. So you take each of these green cones here is one very collimated beam of radiation, okay, that is coming from multiple different external areas on the bottom, on the body, all focused on one area in the lung for a lung tumor here, okay? And you can imagine if you add up all the contributions from each of these beams that we call them in one spot, then you can have an escalated dose at that one spot and you can kill that cancer, and you're getting minimal dose to everything around it, okay? Obviously this is artist, quote unquote, artist rendition, right? The real picture, but it's not so far off from this idea. So medical physicists are doing a lot of these kinds of things. What's the technology that makes this work? Okay, how does radiation work to kill cancer? Okay, you've got radiation dose here, and probability in percent here. Your tumor control probability increases as you deliver more dose. That makes some kind of sigmoidal curve for now, all right? As radiation increases, you're more likely to kill the cancer. Okay, you want to be, if this is the only information you had, you definitely want to be all the way up here. How much radiation should I give? Well, I'll give above this white line because it kills everything. However, let's look at the other factor, normal tissue complication probability. So normal tissue complication also increases with dose. The cool thing is that because cancer cells are cancer, they have often lost the ability to fix themselves when delivered radiation. Healthy cells are really, really cool. They actually can fix breaks. So if your DNA breaks in a cell, the cell can fix that, okay? The ability for the cell to do that is not infinite. So if you deliver a lot of dose, you're going to kill healthy cells too. But if you deliver little dose, you're not going to kill those cells. There is this really nice happy medium right between these two guys, okay? If you can get a dose that's somewhere in this range, you can get maybe 10% healthy cell kill and 90% cancer cell kill. And that's the magic window that we're aiming for. Generally, this window is about 5%. This is about where we can do with cancer therapies. Now, there's all different, there's protons, there's photons, there's pions, there's all different kinds of therapies that you can use to deliver cancer, and it changes how this works. But the idea here is you have about 5%. If you can come up with a technology that has 6, 7, 8, 9, 10%, if you get that, then you're gonna do really well. Now, if the thing is, if you get outside this window, if you deliver more dose to the patient than you expect, then you're in trouble. But if you can get up to, like, if you can do really well in a new technology, you can make the news and you can do really well. And if you mess up this in your dose delivery, if you're a medical physicist and you create a plan that delivers dose that gives more dose than you want, then you also make the news. Okay, and your hospital or your clinic gets shut down and you get fired. Okay, so this is very important. Okay, very important that medical physicists are very critical to the technology in delivering this radiation to the patients, to making sure that everything is safe and effective. Okay, so generally you have photons, beams in the keV to MeV range, radioactive decay, electrons, MeV range, beta decay. Proton beams, pion beams are a little bit historic. Heavy ion beams is the next big thing. Nuclear engineering, if you want to look at like trying to figure out how to do heavy ion beams and like doing shielding for all these kinds of things, that's a really cool place to be. All of this goes into the body, and that is not uniform generally. You have bones that you have to go through, and you have tissue that have to go through. So figuring out how to get this radiation into the body is a hugely non-trivial, and there's a lot of research going forth on that. Okay. So generally, in radiotherapy, you get an image. You see what that image tells you. That image says, this guy's got prostate cancer. Okay, that guy's got prostate cancer. Now what do we have to do? Well, you can go for chemotherapy, you can go for surgery, or you can go for radiation therapy. Radiation therapy is nice because you don't have to get cut in the knife, okay? Chemotherapy, you lose your hair. It depends on what it is. Radiation therapy has its own side effects, but I'll definitely be an advocate for radiation therapy. There's a lot less side effects sometimes than these other treatments. So let's say you want to go for radiation. You have your diagnosis. Then you go to prescribe. So the physician says, okay, I can treat this cancer if I give 15 gray to the prostate. That'll treat my cancer. Okay, I'm going to get CT scans or an MR scan, and I'm going to create a dose plan. That dose plan is what the physicist tries to create. So the physician says 15 gray here. Physicist says I need to figure out how to get that 15 gray there with the technology that I have. So I take the technology for this particular patient, because every patient's different, and I'm going to create a radiation plan. Once I have that plan, I have to set up the patient, and I have to deliver that radiation effectively and precisely. So that's also part of my job. Okay, then we deliver it. Now, a big thing in the field that's kind of going in the next 5 to 10 years is this what's called adaptive radiation therapy, where if you set up and you deliver. What if you deliver some of your dose and then realize that that dose is off? Or what if you deliver, you have a head and neck cancer, you have this huge tumor here, okay? You deliver the dose here. Halfway through the treatment, that radiation is so effective that your tumor has gone from the size of a softball to the size of a golf ball, okay? Your original radiation plan is no longer good because you don't have this softball on your neck anymore. You've got a golf ball, okay? You have to go back and replan. And how can you do that adaptively? That's obviously an extreme example, but that's the kind of things that we're talking about with adaptive radiation therapy. How do you go through the process and create and change the plan as you go? You can change it at the setup place, at the plan, or at the prescribed stage. So adaptive radiation therapy is a huge active research field. Okay, what are the basics of getting this radiation to the patient? So in medical physics, we have linear accelerators. This is the workhorse of what we do. This is the generally considered the 90% of the clinic that radiation therapy uses a kind of linear accelerator. But inside here is very basic technology. You have an electron gun with a waveguide and a linear accelerator here. These electrons generally we put through a bending magnet to do some energy selection. And then they're impinged on a target here. And then once you have a target, you generally get Bremsstrahlung radiation, and that's peaked in the forward direction, depending on the energy, more or less so. So you get a bunch of photons out. Now, you can either leave the filter in and use photons to treat, or you take the filter out and you actually use the electrons to treat. Now, electrons are massive particles, obviously, so they have a low penetration. So they're not quite as effective. So generally, you want to use photons because you can penetrate a lot farther than electrons. So you generally have these photons, and then that comes out a very peaked radiation beam, and you want to actually flatten that out. So you want to have a nice radiation beam across your treatment region. So you have a flattening filter here that's basically the inverse of the peakiness of the photon beam. And then you've got collimators. So you've got these big jaws that basically collimate your beam into whatever size you want. Now, these collimators can be very fancy. They can be made up of hundreds of leaves that move in and out of each other to create these really fancy shapes on the patient, and I'll go into what that is. But this is the main idea. You're taking electrons, accelerating them, hitting a target, made from photons, and you're using that photon beam to treat the patient. Okay. So, if you want to just get an idea, this linear accelerator now moves around the patient to deliver radiation to that patient from multiple different angles. So from this, if you remember back to one of my first slides, you can take all these different beams and you can add them all up like in the brain and get a very, very hot dose target right in the middle and delivering less radiation to the beam. So how does this work? Okay, so we've got a desired dose distribution with something like this Tetris piece. Okay, fancy Tetris piece. Okay, so you have radiation coming from the outside. So you want to collimate that beam a little bit just to get the shape of your tumor. Okay, so your transmitted beam looks like this, and you can do this from multiple angles. So you get transmitted beams that look like this. The problem is if you do that, the actual dose distribution looks something like this. It's not modified. So in the last 10 years, one of the biggest things has been something called IMRT, and that is we have an intensely modulated radiation therapy where we can actually break down that collimation into much more finely tuned pieces. So that now we've got radiation impinging on this multi-leaf collimator that collimates the beam depending on actually the shape that you want. And this ends up in a dose tissue that looks something much more conformal to the target. So this is an active area of research on how to create these and how to use them properly. Okay, so what kind of research projects are relevant? Well, new hardware and software developments, that's what we're always doing. Hardware, software, everything's got to do with that. Image acquisition, image fusion techniques. They need to understand physics and the physics of particle and photon scattering. This is very key to all the kind of technical problems that we're dealing with. Beam profiling, how do you understand the actual shape of your beam, the nature of your beam, and how do you create the most efficient therapeutic beam that you can? Monte Carlo is used a lot in this. I don't know if there have been much experience in Monte Carlo, but Monte Carlo is used heavily in this. And then modeling the scattering, the dose diffusion techniques, optimization algorithms for dose planning. I've done a lot of work in actually optimizing the algorithms for actually delivering the dose and how do you create those plans. So these are all the kinds of things that you can work. Okay. So in medical physics, just to break down before I get into the nitty-gritty of what we're doing at UCSF, dose planning, target definition, dose calculation, radiobiology, radiation delivery, dose delivery setup, tumor tracking. If your tumor is moving inside your beam, how do you compensate for that? Like, do you turn on your beam when it moves inside and turn it off when it moves out? Do you have a robot that follows it takes your whole linear accelerator and follows the tumor as you're tracking it? Lots of cool problems with that. Medical imaging, this is, again, in radiology. There's so much stuff at UCSF. There's 80-something faculty and PhD faculty at radiology at UCSF. A lot of people doing really, really cool work in that. Dose modeling. And just for an idea, a lot of the work and research that we do at UCSF is not necessarily your NIH funded. We have a lot of that research, like your big grants and stuff like that. But we actually get a lot of money from vendors. So vendors, medical device manufacturers, will create equipment and create new technology. And then they have to come to us as medical physicists in the field to say, hey, is this, how do we use this technology? We have this vision, but will it work? And we need to use it in a clinical setting. So myself as a faculty member at UCSF in radiation oncology, I get vendors coming to me and say, look, this is the new device we make. We think it's going to work. We need you to kind of show us what's the best way to use it. We need you to help us implement it into the clinic to make sure everything's safe. And you can have one of our machines for free, but you got to do some work, like helping us learn it, helping us figure it out. Like, we have a lot of things, but you're inventive, you're creative. Come up with new ways to use this machine. So a lot of the money comes from that. And I show this slide just to show that we have research contracts with all these different companies that are doing all these different kinds of technology at UCSF. And these are a lot of the problems that we're dealing with. How do we use technology and advance it to push it past where it was designed to be even? Okay. So that's what's the nature of the scientific research in the field. So let's look at some specifics. What are the UCSF faculty actually doing? Again, this is not my work, so I'm going to be presenting other people's work. I solicited slides from other faculty, and they helped me out on that. And I had to really cull a lot of what I'm going to show you. There's so many avenues of research going on. Like I said, there's 80-something faculty in radiology. There's a dozen or so faculty in, this is just the physics side, in radiation oncology. So I'm just going to give you a taste of the kind of things that we're doing. Okay. This is the deformable image registration group. Okay. So remember I talked about that softball-sized tumor on your neck that turned into a golf ball? Well, what if you got an image of that softball-sized tumor? But on the day of treatment, it's actually a golf ball. But you haven't had a chance, you can't get a new image of that patient for whatever reason. This is a kind of crazy example. Probably never happened, but just to give you an idea. Is there a way to morph that image, the softball-sized image, into a golf ball-sized image in a very quality way, without destroying any of the information that's in that system? That kind of process is called deformable image registration. Or if I had a PET MR on one day, and it's got a very large tumor, and then I have a CT on my day of treatment, and that tumor has gone down because the patient has gotten chemotherapy over the last 2 weeks, 3 weeks since they were imaged on the PET MR. How do I use the information about where that tumor is located on the MR, on the CT that I have today that I'm going to treat that patient with? The CT tumor is much smaller than an MR tumor. So deforming the information in that MR to the information they have in the CT is not trivial. You might think it's trivial. You can come up with an algorithm. I'll bet you, anyone in this room, any of you guys, could come up with an algorithm to take an MR, look at the voxels, look at the pixels in each one, take a CT, look at the pixels, and map one to the other, okay? I'm pretty sure everyone in here has the capability to do that. The trick comes in, what do you do when the tumor on this side is 30 cc, and the tumor on this side is 20 cc? What do you do with those extra 10 cc? They didn't disappear. Or maybe they did. Maybe the tumor got smaller. But in your image set, you don't know where that comes from. So if you have a fixed volume that you're mapping one to the other, what do you do with those? Now, again, I guarantee that all of you in this room could come up with a map that does that from one to the other, okay? But I don't think that you can prove to me that what you did is actually valid, okay? Because what did you do with those pixels? When there's an extra pixel, did you just throw it away? Well, what if that had gotten delivered dose to? How do I count that dose if I threw away that pixel? So there's very interesting nuanced arguments that go on with what happened. So generally, deformable image registration is warping one image to match the anatomy of the other. And it's very big research. Deformable image algorithms are now commonly available in radiotherapy software. But, and here's the huge but, there's no real way to quantify these images. Like, how well is that registration happening? That's one of the, so the deformable image registration group is on the forefront of this at UCSF, is trying to figure out how to do that. So just as an idea, here's a PET CT, okay? And this is a radiotherapy planning CT. As you can see, this is where it's showing up high. This is the tumor here. There's a couple different nodes of tumor. So there's one here and one here. And if you map this straight over, you're gonna have a displacement here between these two, okay? So let's bring in a warped CT, okay? So this is, we take the deformable image registration and we warp these. So we've modified this CT to be more like this CT, okay? Now this will line up much better with here, okay? Now, what we can do is we can look at the difference between whether we did a deformable image registration or without. And if we do that, there are so many different ways of doing that deformable registration. Like I said, if every one of you came up with an algorithm, you could give it to me. And if I execute your algorithm, I'm gonna have way different, my ending image is gonna look way different. So just using two different deformable image registration algorithms, we have this 0.6 centimeter difference between this here. So this is what it was. I used two different deformable image registration algorithms to decide where that PET image is telling me my tumor is on my CT. So this is showing me that there's this much, and these are two commercially available algorithms, okay? This is not just something a student came up with either. These are something that a vendor is selling that's telling me this is good. You use this with my product, and you're gonna deliver radiation. And this guy over here is saying, okay, this is really good. You use my algorithm with my product, and you're gonna deliver good radiation. And then we're sitting here in the middle and saying, well, you're telling me this mapping, you're telling me this mapping, which is true. Maybe neither of them. As a physicist, as a physician, who do I trust? We need quantitative measures of this. So this is a very big reason. Now look at this again. Here's three different users using the same algorithm, because there's a lot of parameters in how you actually map this. Three different users using the same algorithm has mapped out three different actual deformable image registration matrices between these two image data sets. How do you determine who is right and who is better? That's huge, and that's a hard problem, and there's a lot of people working on it. Now, this is on the software side, there's a lot of stuff going on here. So some of the faculty at UCSF have developed a automated tool to do this process, to look at a bunch of, say a dozen different deformable image registration algorithms, apply it to the image, and then give the physician something that's useful. You know what's useful for me? Okay, vendor A says, I'm gonna give you this shape. Vendor B says, it looks like this to me. Vendor C says, it looks like that to me. Vendor D, so on down the line. What I can say is, well, I'll take all these images, okay, and I'll get an aggregate of what all that data is telling me, and then I'll give a 95% confidence level using those images of where that deformable image is telling me I should be. Now that's useful. So coming up with a kind of a tool like that, that's a big deal, and that's really helpful, okay? Monte Carlo simulation in medicine is huge. From beam lines to dose calculations to everything. We have a big particle therapy radiobiology group at UCSF. There's one faculty with a couple of grants. So the idea is, just to give you an idea, age and time of exposure and percentage of people who die from 0.01 gray. If you are 80 and you get 0.01 gray overdosed somewhere, you're probably not going to die of cancer because you're going to die of heart disease before. But if you're an infant or a toddler and you're delivering this stuff to these patients, This is a big deal because you've got 80 years of lifetime to develop auxiliary cancers maybe because of that extra radiation that you got. So modeling and understanding what our accelerators are doing and delivering that dose to that person is very, very important. There's applications in radiobiology. There's applications in radiology, all for Monte Carlo. Every single thing that we touch, Monte Carlo is a big thing. So if you're a Monte Carlo expert and you like doing it, there's a lot of projects to work on right now. Reiki therapy, I'll talk about what that is. We can deliver dose here. No, this is a movie. I don't know if these movies are good play. Okay, good. At least that one worked. Okay, now this is a group formed with one of our faculty at UCSF and a faculty down at SLAC and a couple guys at Harvard. So this is Topaz is a tool specifically for radiation therapy, and it's a Monte Carlo tool to model all these beams. This is actually a linear accelerator beam here, and this is showing you the detail that goes into this modeling. But if you like to do Monte Carlo modeling, if you like to understand what the radiation is doing from a Monte Carlo point of view, there's a lot of problems to be done. You can build your whole linear accelerators just to solve one little problem. Okay, and you can come up. So this is a huge group, and these two guys, Bruce Fadigan and Joseph Pearl, the head of those. Let's see. Okay. And in organ and cellular effect modeling, so okay, now that I have the dose coming out of the machine, what do I do with that dose once it's in my body? How do I figure out photons coming down are going to scatter, going to create, they're going to create auxiliary electrons, they're going to create a lot of other radiation, and that dose is going to be distributed. But how is that dose distributed? And that's a hard problem to solve, because we really want to know if I'm right next to a tumor, I need to know if my dose is going to that tumor or not. So the next step, one of the big things that they're going to do with this Monte Carlo is determine the physical and chemical basis for radiobiological effect with the hope of providing quantitative treatment planning to optimize dose effect and particle theory. This is a huge, huge area of research that could use a lot of people. Just to give you an idea, this is just looking at a 1 keV electron followed up to 100 nanoseconds during the chemical stage. This is using GeoR4, which is the Monte Carlo toolbox that we like to use in medical physics a lot. So first, the physical stage is modeled using GeoR4 DNA physics. 1 keV electron track is fully slowed down and thermalized in a 150 nanometer sphere of liquid water. Yellow points correspond to interaction events in liquid water. And then the next part was that the physiochemical chemical stage is stimulated for the first 100 nanoseconds in individual radiation species, differentiating states. So let's see if I can get this again. Okay, so here's your particle. It's your 1 keV electron going through water. So we're gonna go. Okay, so this is modeling all the interactions that electron has in just water. Now imagine in radiation therapy, you're coming from the outside and you got to go through bone that's very highly dense, then lung, which is lowly dense, to get to your heart, for example, or something like that. So this is very, very important in understanding what we're doing. Okay. Thermal therapy, this is kind of a cool thing, and we've got Chris Diederich is the head of this lab, and he's doing a lot of device manufacturing. So if you like to use devices, he's designing and building and implement. These are interstitial applicators. So applicators that you insert into the breast, for example, for breast cancer to heat it up. It turns out if you heat up tissue and then deliver radiation, remember that little 5% window I showed you with the cell kill and the normal cell complication probability? You can create 5% window into a 10% window. And that's huge, okay? Remember I said getting that 5% is huge. You make it in the newspaper. If you expand that window, and there's so many more possibilities. You can get a lot more effective radiation killing. So this is an interstitial applicator. This is actually for this is for prostate cancer. So this actually goes in the urethra. I know that might not be very comfortable, but the prostate surrounds the urethra. And if you can put this balloon goes up into the bladder and holds it in place, and then this guy actually heats the prostate from the inside out. So that when I deliver my radiation, when it's heated, it's much more effective. This is for cervical cancer here. This tandem applicator goes up into the cervix, through the cervix into the uterus, and this ring here sits around the cervix. So when we can heat the cervix while we deliver radiation to the cervix. So cervical cancer is a huge problem amongst, especially women in the developing world. Cervical cancer is a very big problem, and radiation therapy is very effective. And hyperthermia, in addition with radiation, is hugely effective. So if you can come up with a new device to do this better, that's really, really, really cool. There's a lot of stuff that can do this. This is a pancreatic applicator that they're going to go through the stomach to heat the pancreas. Okay. So they've done a bunch of work on this. We were also using hyperthermia for prostate, hyperthermia for, like as I mentioned, they're looking at pancreatic cancer, cervical cancer, we do all the time. We're always trying to come up with new devices to do this better. Okay, before getting too bogged down in this, I'll go on. We can get into biology too. Okay, so they're looking at small animal studies. So now they're actually using these hyperthermia in conjunction with radiation, and we're looking at actually at the level of small animals to see what the best bet. And I have another slide on this in a minute. But the next steps are large animal to clinical. So how do you take it from using it in a mouse to actually using it in a human? So there's a lot of these steps that we have to pursue. Okay, so the brachytherapy research group. So this is actually one of the slides that died. So I'm not going to do the video. But brachytherapy basically is internal radiation therapy. So I have radioactive seeds that look like about the size of a grain of rice. And if I put those inside the body, I can deliver radiation from the inside out. Normally those seeds are filled with a radioactive isotope. So iodine, for example, iodine-125 or iridium. And I can put those, I can implant those into my prostate, well, not mine, but implant them into a patient's prostate. And then we deliver the radiation from the inside out. You know what that does? That allows me to get my radiation only where I need to treat it. Okay, I don't have to go through the rectum. If I have external beam and I want to treat my prostate, I generally come from the front, the side, from the back. But that means I have to go through my small bowel, my rectum, to get to my prostate. Well, if I'm a patient, I don't really want you putting radiation in my rectum if I don't have to. Okay, so brachytherapy allows the physicians to put the radiation right into the prostate, and you treat it from the inside out. Hopefully they don't crack. Okay. Oh, there we go. Oh, so the movie works this time. It works. Okay, so here we are. We're putting, this is from the New York Times, by the way. They made this really cool thing when okay. So we're putting seeds inside the prostate. This is under ultrasound guidance, by the way, transrectal ultrasound guidance. I'm putting an ultrasound in the rectum. You can see the prostate through there. Here you go. So the ultrasound in the rectum, we inflate a balloon so we can kind of see. Now we can see the prostate. This is the prostate up here on the ultrasound image. So developing the technologies that are doing this is a lot of what medical physicists do. Developing the ultrasound to make the ultrasound better. Developing the optimization on how to plan doing these seeds, where to place all those seeds in the prostate to make it better. So here we're inserting the needles through the perineum, and all of those are created, and these plans are created by physicists. And to make this a better process, physicists have a lot of work to do. Okay, this is one of the things that I work on a lot. Brachytherapy is my specific application, but I won't talk too much about my stuff because there's a lot of stuff going on. But anyway, so that's more or less the end of that. You can always come ask me to see it afterwards. But there's interstitial and there's intercavitary. So intercavitary, like I was talking about, for gynecological cancers, is actually a natural body cavity. For if you're treating the lung, natural body cavity. Okay, anal rectal cancer is natural body cavity. All these places are intercavitary. We can kind of create applicators that fit to what you're doing. Or there's interstitial. You have interstitial for breast. You have interstitial for prostate. So there's the different things. One of the things that I've been working on in the last several years is with a group here at Berkeley in IEOR, and that's robotic brachytherapy. So if you want to take this needle insertion process, and instead of doing it by hand by a physician, if you get a robot to do it, it can be much more precise. So one of the things that we're working on is actually doing robotic brachytherapy. And this is a phantom, a model of the prostate. And here is a robot that we actually that we were testing out some algorithms on how to actually insert these needles into this phantom without. And the idea here was to actually avoid puncturing the base of the penis. So if you do brachytherapy, you're going into the perineum, you actually do have to puncture the base of the penis. Now, some people have erectile dysfunction afterwards. A lot of people don't. But hey, if you can avoid it, why not, right? So we're trying to figure out some algorithms and how to insert these needles without puncturing that anatomical structure. Another thing that I'm working on a lot recently is 3D printing. So can we 3D print brachytherapy applicators that's specific to the patient, okay, and create applicators that are tailored to the anatomy of the patient? This is a skin applicator here. This is a gynecological applicator. These are all gynecological applicators here. This was a template for prostate brachytherapy, but that's one of my active areas of research is using 3D printing for this. So what's the idea? Well, you have 2D contours. So you have this patient, and you have this image, and those contours tell you about the anatomy. So looking at a CT, a physician will come through and they'll map that anatomy out. And those are 2D slices. If anyone has to see a CT and MRI, you actually have 2D slices. Now, to create, from those 2D slices, you can create 3D volumes. And from those 3D volumes, what you want to do is create an applicator that actually fits in the patient. So if I contour this patient, here is the bladder, this here is the tumor in red, okay? Down here is the rectum, and this area here, this is the vaginal cavity. So this is where I actually want to put my applicator, okay? So, but when I contour here, this is what I contour. I want to apply a smoothing function, and then I get something at this point, and then I get something that looks like that. So we have something like that. So this is a 3D model of the anatomy. Now what we want to do is we want to create an applicator where we plan channels to deliver the radiation into this applicator to get as close as we can to the surface here to get to the treat location that we want. So we actually 3D printing is really nice for this because 3D printing allows you to have internal structure that is very well defined. So those catheters have to actually puncture through this whole material. So here, the catheters are actually going through this. If you're going to do this with injection molding techniques, that's really hard because you can't have internal structure. But with 3D printing, you can do this kind of stuff and you can create these custom applicators. So this is hypothetical. We didn't use this on a patient, but this is a hypothetical patient-specific applicator for a patient. We've also done this. Now, this we did do. We had a patient with a oral cancer. So she lost a bunch of her teeth, and she had this oral cancer up in her jaw. And we wanted to get brachytherapy up in there, but you can't like implant the jawbone with needles because it's bone. You can't really get in there. So can we create a custom applicator that fits inside this cavity that she had, basically the cavity in her jaw, very hard cavity. So we ended up creating this technique where we took some images of her, we molded out what we're gonna plan, and then we actually created this custom applicator that was able to fit those brachytherapy applicators into that patient's jaw. So this is kind of this is one of the problems, and this patient was actually treated here, and she's been cancer free so far. So this is only a year ago. So, but we're pretty confident that this is gonna work. Okay, so on to something in radiology. Okay. Again, radiology, very big group here. A lot, like number 3 in the country when it comes to research funding, UCSF, radiology. So there's a lot of projects, so I had to pick just maybe one, okay? This is, John Kerhanowitz is one of these guys, a big wig in the field. He's done a lot for prostate cancer, MR prostate cancer. One of the cool things that they're really doing is called multi-parametric MR. So in MR, you think about it, you just get an image, okay? And that image can give you information about the anatomy. But with multi-parametric MR, you're actually taking information about the image and you're doing spectroscopic information on the image data sets of you. Using different sequences, you can measure different things. You can inject tracer molecules into the patient and see what the uptake is of those molecules in the cancer. Cancer is very good at converting certain biological molecules into other biological molecules. And if you have a map from one to the other, you can see where your cancer is because you can see that the relative abundance of your resultant molecule that's a product of the metabolism of the cancer will show you where your cancers are. So this is just normal T2 weighted MR images. This image here is it's called an apparent diffusion coefficient image. This shows you how much water is perfusing through the gland. And on here I wouldn't say that I can see a tumor here. And I've looked at these images a lot. Maybe you can kind of convince yourself there's something. But if you look at this second type of image where you look at the diffusion of water through it, now, cancer cells are very highly vascularized and they're all kind of messy. The cell walls are not very nice. They're kind of like, they're permeated. There's no kind of real blood barriers to the cells, like things are moving in and out. So you generally get a lot of diffusion of stuff. And if you look at the diffusion weighting, you see there's a very bright spot here that you normally wouldn't see on your just MR image. So you can kind of use this, and then if you scan this using spectroscopy, what I was just telling you about, there's a lot of different methods to use MR to look at that tumor. So here I don't see anything, but here I really see something, and here I really see something. If I was just looking at this, the physician might say, oh, you don't have a tumor. Okay? But if you come to UCSF and you're a patient, and you go to our radiology department, and they run this brand new protocol on you, then they'll say, oh yeah, you wouldn't see tumor, but oh yeah, you have tumor. You better go back and get that fixed. Maybe they missed the first time they did it. Okay? So you come to UCSF and you get your tumor, the recurrence of the tumor gets caught, whereas you went somewhere else and might have gotten missed. So this kind of thing is very powerful. I don't want to go into this too much, but the idea is that you can use, this is mapping out each voxel. This map here is mapped onto this image here. And you can look at each of these sections of the image to look at biological processes and different molecules that are happening. And you can use your MR to find those molecules. MR is really powerful. You can do a lot of really, really cool things in MR that's more than just imaging. And this whole topic is called spectroscopic imaging, MR spectroscopic imaging. John probably took it. John probably knows a little bit about this. But so you can take courses in this at UCSF. So if you're a nuclear engineering graduate student and you want to take some courses in this, you have access to all this stuff. And you can get in touch with these researchers and look at what they're doing. Okay, so then what can we do? Well, let's say this is a prostate cancer, okay? This is something we did in the clinic, okay? This is prostate cancer. We mapped out that prostate. This is the prostate, this is the rectum here, this is the pelvic bones. So we map out each of these things and we look at the spectroscopic image and look for signatures of cancer. Well, these 4 voxels have signature of cancer, okay? So then when I come into the treatment day, I use deformable image registration to map that MR to the CT at the time of treatment. And when I do that, then I can actually boost this area where I know the cancer is. I can't see cancer on the CT. I would have no idea where to put that radiation if I didn't have the MR image, right? So then you boost the radiation to this region, just like you would, like just what you saw in the image here, and then you deliver that plan. So this is just a 3D model of what we're actually trying to deliver. But by doing this, we've actually been able to treat prostate cancer and been very successful. This index lesions dose is was successfully escalated to a minimum of 120% for prescription dose. So here's a region in my prostate where I know I have cancer. So when I develop my plan to deliver my radiation, I'm definitely going to make sure that that spot is not cold. Okay, so that was very cool, and we were able to use that on several patients. Okay, running out of time. So PET MR, the combination of these two technologies is huge. There's a lot of problems in this, or a lot of opportunities to do research in this. How do you fuse the two? Ultrasound. Remember I was talking about hyperthermia? You can use ultrasound probes, and instead of using to visualize things, you can actually focus them and create a very intense heating mechanism using ultrasound. Okay, so you can develop devices that can actually heat. And the cool thing about this is, it's just like any kind of, any kind of mirror. Okay, if you have, if you're a kid and you're frying ants with your magnifying glass. Okay, all right. If you put your hand right in front of your magnifying glass when your focus point is on the ground, you're not necessarily going to hurt, because you're not focusing all the energy on that. But at that focal point, right on the ground, that ant's getting fried, right? Because you're focusing all the sun's rays. Okay. But right between those two places where your magnifying glass is and that ant, you're not getting that intense heat because it's not focused. In ultrasound, you can use the same principle. If you used a phased array that's shaped in some parabolic manner that has a focal spot, then you can use that phased array to actually heat something without heating the boundary of what you're up against. Does that sound cool? Well, now you can deliver you can deliver heat dose without heating the skin. I can put this on my skin and heat a lesion inside my skin without heating my skin. That's huge. That's really, really cool. That's like doing surgery without cutting. Okay? So developing these devices, there's a lot of cool work to be done in developing these kinds of devices, and ultrasound is totally underappreciated. Totally underappreciated. I think there's a lot of work in ultrasound that you can kind of do. Combine it with MR. Okay, I can't get into this slide. I'm going to run out of time. But you can combine it with MR. But there's a lot of different things you can do. Now, they've done a lot of work with parametric MR. They've used hyperpolarized carbon-13 to inject and they can map out where things go biologically using MR. They come up with all these different kind of probes. There's image-guided biopsies. There's PET MRCT. There's a lot of work in not only developing these new technologies, how to make new things happen, but also how do you integrate all those technologies with each other to kind of create a new product or a new thing that we can use to treat patients. A lot of stuff going on. This is just a tip of the iceberg. Okay, now I wanted to finish with just something that I know you guys, I don't know if you met John, but he's in the nuclear engineering program, and he was trying to be one of the pilot students for our PhD program in medical physics, but the reason I bring him up is he worked with Kai, and they worked on a project that is actually related to what we do in medical physics. So this is kind of transition. Can what you do in nuclear engineering, can the stuff that you work, does it apply to medical physics? You as a nuclear engineering, why is there this nice pathway into medical physics? Well, I'll show you why. Okay, John's project, in a nutshell, they're developing a new aperture-based imaging system for high energy gamma rays. Okay, so we want to image high energy gamma rays. How do you do that? Well, you need a detector, and you need some kind of shield in order to focus what you're looking at, because you want to be able to know where these photons are coming But the idea is, these are prompt gamma rays. They can be used either in spent nuclear fuel detection, or when you're delivering protons at a patient, those protons go into the patient's body, and those protons are actually creating prompt gammas. Okay? So those photons can be detected by a detector. And by using this, you can actually map where the dose that your proton accelerator is delivering to the patient is actually going. And that's huge. Again, a huge thing in dosimetry is you can create technology to deliver radiation to a patient. Okay? I can create this really cool accelerator and I can say, okay, these photons are coming at this patient. I think, I'm the vendor, I'm pretty sure I know where this is going. But as a physician or a physicist, I need to know that that's where it's going. There's so many uncertainties, so many errors. I need to develop the technology that allows me to know and verify that what I think is happening is actually happening. So that's what this is. So if I have a photon, what happens with protons is that normally with photons, when you enter the tissue, you have some dose fall off, okay? So this is depth here, 15 centimeters or so. Notice electrons are very short. I mentioned that before with some of the other technologies. Electrons don't go very far. Photons penetration, that's nice, because that means I can kind of add up. Remember that long photo from the very beginning? I can add up all my beams. It wouldn't work if you had to fall off these electrons. Okay, that's nice. What is this curve here? Okay, these are protons, okay, because they're massive. They're what's called a Bragg peak. So as they gradually lose energy going through the body, eventually they come to a point where they've lost enough energy that all of a sudden they want to lose all that energy in a very short amount of time. So you're coming into depositing energy or dose. And then all of a sudden you get this huge spike in peak and then a huge fall off. What does that mean? That means if I have if I have a proton machine and I'm aiming it at someone, if I'm aiming it at my back, I want to treat spinal cancers, okay? I can focus that proton beam so that it comes into my body, penetrates through my back because I'm doing spinal cancer. Okay, and then I can line this peak up right on my spine. So all the dose gets delivered at the spine, and nothing bleeds over into the lungs, into the heart, into the liver, into anything else, because I know it's stopping right at the spine. Great, that sounds cool. Why doesn't everyone do that? Well, it's new technology, it's very expensive, and we're working on it. And there's a lot of people doing protons. That's like the next big thing. Oh, by the way, if you use carbon, this plateau here is like order. It's way down here, okay? Much lower. This peak is way higher. That's the next big thing, too. You can use heavy ions. But anyway, but what if I miss? What if this peak is maybe a little bit further than I thought? Oh man, I'm screwed. Okay. In photons, if I'm aiming here and I move over a little bit on that curve, a couple percent. Okay, I can deal with a couple percent. If I'm with protons, I'm a little bit off that curve, man, I'm screwed. Okay. Yeah, like I said, that's when the New York Times comes calling you and you lose your job. Okay. Okay. So protons are very cool, but we really, really need to know where this Bragg peak is. Okay, so come prompt gammas. If you can measure the prompt gamma production, this is the measure using the detector that they built, okay, for the prompt gammas. And they're localizing where these photons are coming from. It turns out that theoretically, you expect these prompt gammas to be just shy of the Bragg peak, okay? That's what you expect theoretically. And depending on the actual atom that they're coming from, you get different shape curves here. But theoretically, this is just shy of the peak. But using that theoretical understanding, you can map your prompt gamma detection to where you think your dose is going to verify that you're actually delivering the dose where you're going to go. If you expect this to be, a centimeter off the peak, and you're measuring it 2 centimeters from where you think you're putting your peak, whoa, maybe there's a setup error, maybe the energy on your proton accelerator is a little bit off. There's a lot of different things that are going to happen, but at least now you know that you're wrong, so you can go back and check it out. Okay, so this is a project that John and Kai and I didn't meet him. I never met you. Lucian. Okay, they're working on, and it has very real applications in nuclear engineering and in medical physics. And this is just one example of developing hardware like this. Huge overlap in what you can do. Because you're dealing with radiation, you're dealing with radiation protection, you're dealing with how that radiation interacts with the material around you. Okay? All right. Okay. Not going to go into that. Okay. Now we're getting to the end. So what we want to talk about is I want to get to, can I pursue a career in medical physics? But to get there, I just want to talk about who are medical physicists. Okay? So who are medical physicists? Well, I kind of mentioned this number before. There are, at UCSF, there's about 30 30 faculty in radiation oncology. Now, the physics faculty work very closely with the physician faculty. So the physics faculty here is about 1/3. Okay? So we're working very closely. The nice thing is these physician faculty are always coming up with ideas. They're pushing the boundaries. They're telling me, okay, as a physicist, I can come up with this cool device that delivers this cool kind of radiation to this patient and say, hey, this would be great. And let's have a physician who's there who's saying, oh yeah, I really want to use this in my clinic. It's not so useful. So the nice thing is to have interaction with the physician. The physicians are coming along and saying, hey, you know what, I wish I could get the dose here without getting it here. I need a technology to kind of figure this out. Well, then you get to interact with that all the time. And you get to work with the physician, really apply real problems. He's like, my patient that I'm going to have in 3 weeks really, really needs this. Now, 3 weeks is a very short time to come up with the technology. But maybe that patient might not work. But the next patient that comes down the line in a year, you could have a solution for that problem. Okay? And that's one of the things that I like about my job the most, because I'm solving problems that are real in the treatment of real people, in the treatment of real patients, people who might not survive to have another year if they don't have the technology that we're developing right now. Okay? So that's really, really, really influences why I like going into this. Okay? So huge departments to work with, and just for breakdown, okay? Radiation oncology. Where did our radiation oncology faculty get their degree? Okay, of these 13, one was nuclear engineering, two were nuclear physicists, 2 were high energy physics, 2 were bioengineering, 1 was condensed matter, 1 was applied physics, 2 were radiation physics, and 2 were medical physics. Only these bottom 2, these 4 of those 13, are actually medical physics, right? The vast majority of the faculty at UCSF don't have a background in medical physics. Now, why do I bring this up? You go some places, and you'll get a degree in medical physics, and then you'll go and you'll become a faculty of medical physics, or do research in medical physics. That's great, okay? We actually benefit, we think, from having a very diverse background. People who have the experience of having a nuclear engineering PhD, having a high energy physics PhD. We bring in tools to the table or ways of thinking that are a little bit different, okay? So there are a number of good places out there that value the fact that you got your degree in something other than medical physics. And that is a very high value, because it's telling them, you got your degree in nuclear engineering from Berkeley. Oh wow, you must really, really know your hard science. You're not just medical physicists. You know how to get a PhD in nuclear engineering. Like, that's hardcore. That's not just a fluff degree. All right. Oh, yeah, okay. Anyway, that matters to a lot of people, and that makes a big difference. So I guess the point I'm trying to make is we actually value. If I have a faculty, someone who's applying to the faculty of medical physics, I like the guy who's got the engineering background rather than the medical physics background. You can learn the medical physics. You can't learn the hard science. You can't learn how do you do science. How do you solve engineering problems as well. Like, if you go to a good program, you have a really good background in that hard science. That matters to me more than during learning the applications to medical physics. All right. So, just some demographics. So this is from a 2010 AAPM survey, degree discipline. So you can see bachelor's, we have non-clinical. This is non-clinical physics. Okay, this is like medical physics bachelor's. This doesn't really even exist very much. I don't even know where this 2% came from. But then nuclear engineering is not small. Okay, 8.2, 11.3, that's your bachelor's. Then you get to master's, and this is kind of where the clinical medical physics come in, because there are master's and PhD programs for medical physics. That comes in, but there's still a lot of these people who have master's. And if you look at the PhD level, and you got a lot. The thing is, this master's thing, there's a lot of people who get a master's in medical physics and then go work in a clinical job with your master's. Because if you work at Kaiser, you have to do your machines, you have to understand the technicalities, you have to understand the didactic coursework of what it is to be a medical physicist, but you don't have to have the penchant for doing like kind of research or kind of doing that kind of problem solving. So you have a lot of these physicists who get the master's and then go on to be clinical medical physicists. But if you want to be in the faculty at some place like that, then you get your PhD. Okay, now job description: primary clinical, primary academic, primarily project R&D. So this is mostly industry, administrative, regulatory. Okay, so this is just small numbers. This R&D, this thing is a little bit small in this. If you look at some other surveys, this has an N of about 2,000. So, but I think the problem is it's biased because this was done by the AAPM, which is the Organization of Medical Physicists. If you're in industry, you're less likely to kind of be as active in AAPM. So, you might not have. So I think this is a little biased. This 7% is a little bit low. But anyway, a lot of people are working in clinical. Not a trivial amount in academic and doing kind of research, but a lot of these jobs are in the clinic. So you're definitely working with physicians and working on hands-on kind of stuff, or you're doing kind of research. Okay, now, med school or university hospital, that's kind of like the biggest one if you're a master's, even bigger if you're PhD. Cancer centers, rather much bigger here. But you get the idea. Industrial, again, is at around 6%. Again, this is so, but just an idea of where we work. So you can work in a cancer center, you can work in a med school, you can work in an industry, you can work in a medical physics consulting group. So I'm an entrepreneur and I want to create my own business. I create a medical physics consulting group and I go out to the smaller clinics that only need me for 1 month at this time because I got a new piece of equipment and I'm commissioning that piece of equipment. So that's kind of your idea. Go for it. Okay. What's the last one? All right, primary discipline. Okay, so just to give you a breakdown, radiation oncology is kind of like the big one here, but radiology, diagnostic radiology is big. Nuclear medicine and radiation safety are kind of smaller, but they're kind of niche markets. They're not where you're doing a lot of the kind of like the hardcore workforce clinical work. Okay, so in a group, pursue a career in medical physics. So, kind of alluded to it in the other slides. Historically, medical physicists had a disparate training, a wide range. You had people who had nuclear engineering, you had people who had medical physics, you had all those things. And this is mainly, and a lot of people actually didn't have any experience in medical physics in the classroom. A lot of these people, if you look at someone 10 years older than me, it's kind of when the kind of threshold was, you were learning on the job. You got your degree in nuclear engineering, and then you kind of met someone who is doing this stuff in the clinic, and you're like, hey, I can do that, and, I got a job, like I'll show you what to do, and then you start to do it. But since you had the kind of the background in the science, you're technical, you can kind of do it, you can pick it up. They're trying to create a much more finely tuned method or procedure for people who are being trained in the field to follow, so that they can have a bit less variance, okay, in what people's clinical or what people's aptitudes are when they're going in. I tend to like variance because I feel like people get a lot of, you get a lot of those. It's like what it's what the .comers do, right? You put everything in the cloud, and you get that one guy who's totally socially awkward and sits in his garage, but it's a genius at that one thing. Okay, all right, that's a little bit of an example, but I kind of like variance. But they're kind of trying to get rid of some of this variance in order to have a very well defined. At least everyone who makes it into medical physics and practicing medical physics has a very strong core of what it really means to be a medical physicist. So clinical training used to be on the spot, and now a residency is required. So if you have any physicians, or people, you go to med school, then you go to your residency, and then you practice. The residency, the med school, you learn all the theory, anything that you need to get out of a textbook. The residency is very much, I need to learn on-the-job training, what I'm going to be doing. Now we're going to have to do residencies in medical physics. Now, medical physics residencies have existed for 40 years, 20 years mainly, if you look really far back. But so they're around. They're not new, but everyone is now going to have to do it. In order to practice medical physics, you have to go through a residency. And a medical physics graduate degree is now required to get into a residency. So what does this mean? Okay, here's your goal. You want a career in medical physics. Okay. You have a bachelor's degree, all right? Well, in order to get into medical physics, you have to go through residency. This is definitely a barrier to entry, so you got to go through this path to get here. How do we get there? What's this middle part? Well, you can either get a master's in medical physics, but I'm not going to talk about that because that's kind of pointless for you all because you're looking at it in nuclear engineering degree. So your master's in nuclear engineering, for example, and that obviously feeds into a PhD. So if you're in a PhD program, the master's comes along, right? You need to have a PhD in a related field that's accredited by our national standard organization that accredits programs. In order to get into residency, you have to go through an accredited program. That's what we're working on here, is to create the program here that's accredited, that allows you to do this. Now, there's a couple other kind of circuitous ways you can get to this side, so I'll put them on for completeness, but this is what we're gonna be doing. You got your bachelor's, you're gonna get your PhD in an accredited program, and then you're gonna go to a residency if you wanna do it. Okay, obviously, not all you have to go into medical physics, but I'm just saying it's an option there if you want it to be. How I think we're gonna structure it is maybe as part of the minor, that could be how your coursework get filled in, okay? All right, there are other paths, and we can talk about them if you're kind of interested, but like I said, that's kind of out of the scope of what I think. Now, the one thing I want to say, you don't have to go through residency if you want to live on NIH funds. Okay? You can get your PhD, okay? And then you can go into academia as a medical physicist. For example, Stanford has some positions, faculty positions in radiation oncology that are not clinical, that are purely based on their academic research positions, and you're applying for R01 funds. And you're doing big projects. You're developing the next tabletop proton accelerator, something like that. You can do that without a residency. But that's still within that realm of what you need. You can do it if you want, but that's not going to be working yet. Okay. So this is the path that you want to follow. We can fill this once we get this program, and we're well on the way of getting this program accredited. So that's one really nice thing that we're going to have. The only other thing I want to mention is that between graduating and having a career, you have to pass boards. So there's board certifications, just like they have for physicians. And you know what? If you've been through the programs, these are not a big deal. If you've been through your residency, these are not a big deal. But I'm just putting it out there that there's this board certification, just like they have for physicists, just so it's like basically like qualifying exam, except they're much more inclined to qualifying exam can be really hard. These board exams are not trivial, but it's one of the processes. Okay, so my last slide. I went a little bit long, but we also didn't start until Berkeley done. Okay, so our accredited joint program in medical physics currently in advanced stages of development. We're working to put all those together. We'll be applying for accreditation this year, and we'll do coursework in medical physics related to courses at UCSF, and probably be what you choose as your minor or your focus within the nuclear engineering. The thesis, oops, crap, go back. The thesis, this must is wishy-washy, okay? We want to do a thesis in medical physics if you're going to be part of the program, because that's part of the draw that you can do with medical physics thesis. But technically, because of the paths, there's a little bit of wiggle room. As long as you have the didactic coursework done, your thesis can be we can make it work, right? So just to be aware of that. But hardware design, imaging protocols, dose delivery systems, dose optimization algorithms, software applications, all of these kinds of things can qualify as thesis topics for what we can do. And again, it's not finalized, but what we're going to do is we're going to graduate with a degree in nuclear engineering, PhD degree in nuclear engineering, with a certificate saying that you have a specialty in medical physics. And that certificate is the power that you have in order to get into your residency programs. So if you want to get into residency, and that fully qualifies you for residencies. All right, so that's it.